Welcome to the first session of Wednesday. Our speaker is Jonathan Oppenheim, and he's going to tell us how the second law of thermodynamics is not an inequality, but actually equality. Please.
Thanks, Fernando. So I'd like to thank the local organizers and the program committee for the chance to present this work. It's joint work with the UCL group, so Luis Massanas, and two students, Alvaro Alhambra and Chris Perry. Chris is now at the University of Copenhagen, and Alvaro Alhambra will be graduating shortly. He's a brilliant researcher, and if anyone's looking for a postdoc, should act quickly. The work we're presenting appeared in kind of two publications together in PRX. I'll mostly be talking about the case of fluctuating work rather than fluctuating states. I'm not presenting this work because my contribution was significant, but more because my co-authors were too embarrassed to present it. Alvaro and Chris are here, and they'll answer any hard questions. Good. So since we're in a friendly audience, I can probably show you this. It's a map by Rob Speckens, and I guess the general idea is that we can use tools in information theory to understand lots of different areas of physics, and we've heard about many of those different topics throughout this conference. I'm particularly interested in understanding thermodynamics, so this little corner of the map here. It's a corner populated by a number of different tribes. They are engaged in skirmishes where mostly they reject each other's papers because their paradigms are slightly different. And I guess the goal here was to, in particular, well, there's two, I think, communities of the quantum information thermodynamics community, which uses tools from quantum information theory. And then alongside that, there's this big community we'll call stochastic thermodynamics. So people that study things like the Crookes equation and the Jarzynski equation. And the two fields have kind of going along side by side. There have been some attempts to bridge the gap, but the goal here was to understand the relationship between the two fields. And of course, once you can do that, then one's able to generalize their results and extend them further. So that was the goal. One of the main goals of this project was to see the relationship between these two different fields. Along the way, we'll find some new results in majorization theory and also see that our results have application to finite time thermodynamics. So many of you, but not all of you, were at Lydia Del Rio's tutorial on thermodynamics. So, and you probably all know of Landau erasure, but just to quickly remind everyone, thermodynamics is a kind of information theory. There's a strong relationship, and it goes back to Maxwell, Szilard, and especially Landau and Bennett. So for example, if we have a bit, it's in an unknown state, then that has to be represented physically. And so if we don't know what value the bit is in, and we want to erase it, then we're going to have to physically do that. And Landauer said that that cost kt log 2 bits of work. So we, for example, imagine a box with two partitions and an atom inside the box. If we want to erase it, we're going to have to remove the partition, because erasing it means we put it in the 0 state, so on the left here. And so we need to push in the piston, and that costs kt log 2 bits of work. Good. So I guess the question is, what do we mean by, the first question we can ask is, what do we mean by kt log 2 bits of work? And so let me ask you a few questions about what we mean by kt log 2 bits of work. And let's go to the limit of perfect erasure. So a small pop quiz in the morning. So what do we mean by the work is kt log 2? I guess the question is, how many of these statements are true? The first one maybe is fairly easy. The work is kt log 2 on average, but there will be fluctuations around this value. So how many people think that one is true? And how many think it's false? A few think it's false. Okay. I'm actually going to tweet the quiz so that way people can answer there, because people don't seem to be answering here. Yeah, the word perfect is a giveaway, isn't it? And how many think that if we use slightly more than kt log 2 bits of work on average, then sometimes we'll actually gain some work when we erase? How many people think that is true? Few people. How many people think it's false? Okay, and no one put up their hand. Maybe you don't want to answer, but maybe also we don't know, and that's, I think, the case. We don't actually know the answers to these questions. We sometimes know in the case when we are only allowed reversible operations, but in general, we don't know the answer to the question. And so this work will answer some, I think, very basic questions about Landau erasure. Next is maybe none of these statements are true. And this quiz is undecidable. The correct answer is actually, it's not E, this quiz is undecidable, it's just that the quiz is undecidable. And we'll be able to show that the first three are false by deriving this relationship here. So this is, I think, one of the main, at least classical results of this paper. I'm going to show you some classical results and then show that they follow from some quantum identities. So the main result is this one here. And if you look at it, it looks a bit like the doubly stochastic condition that you're used to in many aspects of majorization theory, but it's got an extra Gibbs factor here with some funny W term there. And that W is the fluctuating work. And what this set of relationships are, they're a generalization of double stochasticity to the case where you have fluctuating work, and we'll show that they arise in the context of thermodynamics. What that means is if you have an erasure process, you're going to get two equations which tell you what kinds of value, put constraints on the kinds of work that you have. And I'll go back to this picture. I'll come back to this picture towards the end of the talk. Okay. So the main results that I'll present is that we're going to look and see and build a bridge to the field of stochastic thermodynamics. We'll be able to strengthen some of the results there and learn some new things. We're going to do that by generalizing the notion of doubly stochastic maps and majorization. One of the results we're able to derive is a second law of thermodynamics as an equality, and we'll do that by introducing something called a fine-grained free energy. And later we'll even see that there is a kind of a quantum map which looks like which helps to find a free energy, an operator. And the main result is a fully quantum identity which allows us to derive very quickly in a line or two various results from stochastic thermodynamics. If I have time, I'll talk about how we can go beyond this. Now that we kind of have a framework for understanding stochastic thermodynamics, we can use it to understand not just fluctuations of work, but also fluctuations of states. And we'll see that it has some impact on some recent results proving and quantifying the third law of thermodynamics. So just an outline, I'll review thermodynamics. I'm not going to do it, I'll do it very quickly because Lydia Del Rio did a nice job of it in the tutorial, but I know not all of you were there. And then I will present these equalities for work fluctuations. All right, so we're interested in how the work fluctuates during a state transformation. And then I'll present the quantum identities, which give you these work fluctuations, and then I'll end with some open questions and kind of an overview of some of the research directions we're going in. Good. Okay. So you all probably know the three laws of thermodynamics. A lot of you are in computer science, so I don't take that as given. But the three laws of thermodynamics, there's four of them, and we're interested in, for the purposes of this talk, the second one, the second law of thermodynamics, which, as you probably know, is that if I have a cup of coffee that's hot in a cold room, then it's very unlikely that it's going to heat up. So very unlikely means we're talking about quantities on average. And it's also important that we talk about a cyclic process. So we have some environment or some heat bath and it returns back to its original state. In the quantum regime, there's questions about what we mean by a cyclic process, which are unresolved, actually. And you can quantify the the second law of thermodynamics as an inequality. So this is the inequality that we'll later find out can be derived from an equality. And it's just that the work has to be less than the change in free energy. So this is about state transformations. We can go from one state rho to one state sigma if and only if the work is less than the change in free energy. And the free energy is just the average. It's an average quantity, so it's the average energy minus the temperature of the heat bath that my system is in contact with times the entropy. And in this case, we'll use the von Neumann entropy, but it could also be a Shannon entropy. And for reversible processes, the work is just the change in free energy exactly. But here we're interested also in irreversible processes. And then we have an inequality, so the average work is strictly less. And what we're going to find is that this average inequality is just the first order term of an equality which we Taylor expand. Okay. I don't mind questions, by the way, if people have them. So I think like a lot of people, when I learned thermodynamics, I didn't understand very much about it. And I think that was largely because I was never, in most textbooks, when you learn it as an undergrad, you are never told what thermodynamics is, all right? You know that there's some isocores, there's some adiabats, there's all kinds of isotherms, and you're never actually told what you're allowed to do, what the rules of the game are. So I think one of the things that quantum information theory brings is we first define this resource theoretic approach where we first say, the first thing we need to do is we need to define what thermodynamics is. We need to say what the rules of the game are. And these have been developed, there's slight variations in them, but I'll call this one thermal operations. It's the following. I start off with a density matrix rho, some system rho, in state rho, with a Hamiltonian HS. I'm allowed to add some free state, all right? It'll turn out that this free state is the Gibbs state, is the thermal state. So I'm allowed to put my system in contact with some free state that is just lying around. And you can, in fact, derive that it has to be the thermal state or the theory becomes trivial. And next, I'm allowed a work system. Okay, for the moment, we'll just have I'll specify this in more detail in a moment. And then we want to put these all into contact. And there's lots of different ways, different paradigms, and different ways of doing it. But the one we're going to choose here is we're going to allow energy-conserving unitaries. This is just like the first law of thermodynamics. So we're going to assume that the unitary has to commute with the total Hamiltonian of the system. The reason we demand that, it seems like a very restrictive condition, but it's not actually. The reason we demand it is because we're interested in work. We're interested in how much energy we need to perform a state transformation. And if we're interested in energy, then we have to make sure that we account for all forms of energy, and we have to make sure that you don't smuggle energy in. So we want to make sure that your operations conserve energy, which means that any energy which is no longer in the system in Bath must have been transferred to the work systems. That way we get a proper accounting for work. Right? We're allowed to trace out. For the purpose of this talk, I'm going to imagine that I think I'll imagine that the initial Hamiltonian is the same as the final Hamiltonian, but we can actually easily, in our paper, we deal with changing Hamiltonians. So you can imagine that the final Hamiltonian is different to the initial Hamiltonian. You can account for that just by adding a switch. And finally, I'm going to assume that the operation, the unitary that we're doing, is translation invariant on the weight. And the reason I do that is the following. Work is a process, right? We can think of work as we have a weight in the classical case, and we want to raise or lower it. We want to do work on the weight, right, or on our system. So it's some sort of a process. And in the process, we don't actually care where the weight is initially. What we care about is how much we can lift it up by, right? So we care about the differences. And so because we care about the differences in the height of the weight, we just only want it, we want to make sure that we should say that it doesn't depend on the state of the weight. All right? So in this case, what we'll do is we'll take a Hamiltonian, which is unbounded from above and below. That's an idealization, but fine in most practical situations. And now we have this raising and lowering operator, and we want that we commute with raising and lowering of the weight. All right? And that gives us a number of things. what it means, for example, is that many different paradigms that people consider in thermodynamics are equivalent to this one. What we want is that we have the broadest possible definition of thermodynamics. Why do we want that? We want it because we want to derive fundamental limitations on what you can do. And so we want to make sure that we give the experimenter the most power possible. And that way, we're guaranteed that if we derive some limitation, then that limitation will hold in anyone else's definition of thermodynamics. All right? You also might want to consider more restricted operations. So for example, you can consider very crude control of your system, and actually even very crude control, at least in the classical case, is equivalent to this very strong definition of thermodynamics that I just presented, where we allow the experimenter to do everything. So it includes, for example, some people say, well, you should just add you can't do a unitary, you can just stick in an interaction Hamiltonian. It includes that. It includes people that just look at changing Hamiltonians. It includes paradigms where people have an implicit battery. In other words, they just say, I do some unitary, and all I consider work to be the change in energy of the system in Bath. So we here have an explicit battery, an explicit work system, because we want to talk about the physical quantum properties, perhaps, of that battery. But our paradigm includes the implicit paradigm as well, which is what people do, for example, in the stochastic thermodynamics community. Okay. And now, having defined what we mean by thermodynamics, we can now ask the questions. All right? So we've defined what we mean by thermodynamics, and now we can ask, what is the cost of the state transformation? And that is the second law, right? It's telling us how much work we need to do any particular state transformation. And when we say work, we could mean many things by it. Often for quantum systems, little autonomous machines, there's no external work system, so you're dealing with a case where there's no work. We could imagine that the amount of work we want to consider is a deterministic amount of work, because we're dealing with quantum systems, and that's kind of a reasonable thing to sometimes look at. We may be considering the average case, and here we're going to consider fluctuating work. Right. Good, so now, having defined thermodynamics, I want to derive the kinds of second laws we can get, the kinds of restrictions on state transformations. So let me remind again that in the classical case, we have this inequality. The average work is less than the change in free energy, and there's only one, and it's only an average case thing. And here, what people found was that there are, in fact, many second laws if we go to finite-sized quantum systems or finite-sized systems in general and don't take the thermodynamic limit. So let me first present a kind of a toy model, just a toy thing of, we called it sometimes thermodynamic for children, or noisy operations. The Hamiltonian is 0, so you're just dealing with, the Gibbs state is just the maximally mixed state, and you're just allowed to add the maximally mixed state, do a unitary, and trace out. And what you can show is that you can go from rho to sigma if and only if rho majorizes sigma. All right? So an average is, we know that it's just the entropy that tells you whether you can go from one state to another. But in the finite size case, we find that it's majorization, which tells you whether you can go from one state to another. And majorization is just that here we just only care about the probabilities. So I order my probabilities or my eigenvalues from largest to smallest. And then I look at the sum of the K, the L, well, that should be L here, I guess. I look at the sum of the L largest probabilities. I compare it to the L largest probabilities of my target state. And if the sum of the probabilities or the eigenvalues is greater for the initial state than it is for the final state for all values of these sums, then we say that rho majorizes sigma. And we can think about that graphically. So here we plot the probabilities P1, Q1 in decreasing order, so P1, Q1, P2, Q2. And now we can integrate. So we can now look at the sum of the largest eigenvalues, and here is the sum of the first 2 largest eigenvalues, and the sum of the next 3 largest, the 3 largest eigenvalues, and the sum of the 4 largest eigenvalues. And majorization, as represented graphically, is just that the curve of the initial state is above is always above the curve of the final state. All right, so nice graphical interpretation. And that just corresponds that just corresponds to the fact that in noisy operations, you can go from rho to sigma if and only if your map is doubly stochastic. Okay? Now let's go to the case where we are no longer doing thermodynamics for children, but have some energy levels. And it's also given by a slightly different form of majorization. What you do is, instead of ordering the probabilities or the eigenvalues from largest to smallest, you put in a inverse Gibbs factor, and then you order them from largest to smallest in terms of these combined quantities here. We call that beta ordering. And now, for each of these, and now what you do is you just plot you order them, and the ordering now corresponds to a slope. So you can see that the slope is getting smaller and smaller. So we plot these in terms of their decreasing slope. Along the x-axis, we plot the inverse beta factor, and here we plot the probabilities. And so once again, we say that we can go from rho to sigma if and only if the curve, the thermomajorization curve of the initial state is above that of the target state. All right? So this is a generalization of the majorization condition, and it corresponds to, Joe Rennes has called this Gibbs stochasticity, because instead of being doubly stochastic, the rows sum to 1, but the columns have to sum to give you back the Gibbs state. Right? It's like Gibbs-preserving. And now what we're going to do is we're going to generalize this notion of Gibbs stochasticity to the case of fluctuating work. I should also say that if you allow deterministic work, then you're allowed to basically move points to the left. We'll see that later. Okay. So I will derive this for you, but now take it one of the results we derive, this classical result, is that we can go from rho to sigma in the case of fluctuating work if and only if this condition is met. It's like a generalization of Gibbs stochastic, or a further generalization of majorization. So in addition to preserving the Gibbs state, the thermal state, you also have this additional term W here, which also is allowed to fluctuate and in some sense helps you, it's assisted, helps you achieve your goal of going from rho to sigma. Okay? So it's this. So this is I guess the main set of equations we derive. Notice this top one here, we have D equations, so one for each level in our system. And what that means is that the equalities that people had derived in stochastic thermodynamics, like the Jarzynski equation, in fact, this gives you a lot more constraints. So it tells you all the constraints that you have. It's a necessary and sufficient condition, giving you all the constraints you need to go from rho to sigma. Okay. Let me now show that from this, it's just a 2-second derivation by just tracing out some information to get the second law equality. All right? So what we're going to do is we're going to define, remember the free energy was the average energy minus T times S. We're going to define a fine-grained version of that. All right? And this fine-grained version, if we average it, it's going to give us the standard free energy. But here it's going to appear in the exponent. So what we do is we take our generalization of double stochasticity, and all we do is we multiply and divide it by P of S, the probability of the initial state being in state S. Multiply it by the probability on both sides of the final state probability distribution, and now take the sum over all S prime. All right? And if we do that, and all we've done is we've taken this doubly stochastic condition here, multiply it by this thing here, and taken the sum. And if we do that, we just use Bayes' theorem, and we get the second law equality over here. All right? And this second law equality, it's appeared in the literature before. in terms of, people have derived it assuming some kind of stochastic processes or performing measurements. So classical derivations. Here we're able to get a fully quantum derivation of this second law equality. And notice what's nice about it is that it gives us corrections to the second law. So we can take this second law equality, we can Taylor expand it, and so to first order, we get this, the first term only, and that's just the standard second law. But we also, if we take n odd, we get these higher order corrections in terms of beta, the higher order corrections to the second law. So it's a more precise version of the ordinary second law inequality. Okay. Good. So now let's go back to the case of Landau erasure, which we had at the beginning. So this is just Landau erasure, and there's 4 possibilities in the deterministic case. Initially, the bit is in the 0 or 1 state. It has probability of half of being in either. We don't know which. And what we want to do is we want to bring it to the 0 state. So we want to bring it here, and we have some probability of failure. All right? Now, of course, you can also consider non-deterministic processes where the work doesn't depend on whether you're going. So here we have a different amount of work depending on whether we're going from 0 to 0 or 0 to 1 or 1 to 0 or 1 to 1. But you can imagine that you have a non-deterministic amount of work for Landau erasure. It turns out to be equivalent to what I'm going to say here. If you look at our Gibbs stochastic condition, you get these 2 conditions here. And in the case of perfect erasure, we can plot the work going from 0 to 0 with the average case. And what we find, 2 things. One is that we only are able to achieve kt log 2 in the case where both work values are kt log 2. Okay, so we can only approach the ideal cost of Landau erasure on average when there's no fluctuations whatsoever in the amount of work that we have. All right. And what's more, we see that the work can never get positive. It's always negative. So there's no way, even if you invest a bit more work in certain cases, there's no way to have it so that you sometimes erase a bit and occasionally get work out. Right? So using this relation, we get some additional insight into Landau erasure. Okay, and that's why we're able to show that these 3 things are wrong. Part of the reason that we can't get perfect erasure, you can see that in the case where the failure probability goes to 0, we have to allow arbitrary large fluctuations in work when we fail. All right? So the work fluctuations have to be arbitrarily large if we want to be able to erase perfectly. Okay. So just to review, we have different kinds of majorizations and maps. In the case where we have no Hamiltonian, thermal operations correspond to doubly stochastic maps. If you have a Hamiltonian, you have Gibbs stochastic maps. And in the case of fluctuating work, you get this generalized Gibbs stochasticity. From a diagrammatic point of view, just like in the case of thermomajorization and majorization, in the case when the work is just a difference of 2 quantities, what it corresponds to is that we want, say, the red curve here, the initial state, to thermomajorize the target state sigma. So we want the red curve to be above the green curve. It's not. So we can ask, how much work do we need to make this transition happen? And in the case of fluctuating work, in this case, what you're allowed to do is move the points to the left and right, and the amount by which you scale these points, this diagram, corresponds to how much fluctuating work you have to invest or get out. So what we're going to do, we can derive these classically, but what we're going to do is we're going to derive it from a fully quantum identity. And that's the fully quantum identity here. It looks, it actually should look like this is a kind of has a similar form, at least formally, like the Gibbs stochastic, the generalized Gibbs stochastic condition. All right, so, and you remember that we had this thing called the fine-grained free energy. So instead of the free energy, which was an average quantity, we had this fine-grained free energy, which was a different quantity for each energy level. And on average, it gave us the ordinary free energy. Well, here we have an operator. It's some kind of a map which acts on our state rho. So you have a state rho. You apply this map, which is we hit rho by an exponential on both sides with a beta h. And that is kind of an operator version of the exponential of the free energy. Right? And with that definition, we're able to now, here we have the thermal operation. So the thermal operation is gamma here. We act a unitary on the system in bath and trace out the bath. That's the thermal operation here. And so you have a free energy, a thermal operation, an inverse free energy, and that has to equal 1. All right? And now taking this quantum identity, we can look at what happens if the initial state is classical. We don't need the final state to be, just the initial state has to be classical. If the initial state is classical, then we recover the classical Gibbs stochastic condition. And we do that just by imagining that the initial state, we can just write it out in terms of its eigenvectors. It's diagonal in the energy basis. And if we do that, then this thermal operation, gamma, it just becomes a conditional probability distribution. Right? So in the classical case, we recover the Gibbs stochastic condition. I should also say that about a week or two, let me give you these ones. I'll get to a moment some other kind of quantum identities called like a quantum Crookes relation, which Johann Auerberg found about the same time as our one. In fact, a week or so before. So let me kind of briefly go over the proof of the quantum identity. What I want to do is I have my work system here, my state here, and now what I want to do is I want to act this kind of map which looks like the free energy, which kind of converts this to a free energy, a free energy operator. I want to act my thermal operations, and I want to then close it off by acting the inverse of that map. And all I really do is I write out, this proof relies on very simple things. It's just, each line is just a different property of thermal operations. So here the property we use is that a thermal operation is just a unitary, and adding the Gibbs state as a unitary acting on the Gibbs state, the system and weight. Here we use the fact that here's just a rewriting of the above equation. Then we use the fact that the unitary conserves energy, so we can commute this thing through the unitary. So this map that is the free energy commutes through the unitary. And finally, we use a fact that a thermal operation or any unitary which is translation invariant on the weight preserves the identity. So we just use the main thing is we just use a few simple properties of thermal operations. And that lets us derive this fully quantum identity called this generalized Gibbs, a quantum version of the generalized Gibbs stochastic equation. You can easily derive quantum identities which formally at least look like the second law equality, look like a Jarzynski equation, look like a Crookes equation. So Johann derived a Crookes equation, and this a Crookes equation which is only on the weight. Here we're able to derive a Crookes equation which is on system and weight. As far as we can tell, these results are non-overlapping. Neither one implies the other. And it's a nice, the Crookes equation is nice written in this form, especially if you're interested in the Petz recovery map. And I know some of you are, I'm interested in the Petz recovery map. And what the Crookes equation basically is telling you is that a thermodynamic process, if we look at the, it's equal to the so if you look at the dual of the inverse thermodynamic process, it's equal to the Petz recovery map. I don't know what that means. It seems like a deep fact about the resource theory, but it's quite intriguing that we get that. So the dual of the reverse thermodynamic process is the Petz recovery map of the thermodynamic process. Now, if we take these different quantum identities and go to the classical limit, imagine the initial state is classical, here's where we get these classical equalities. So we get the second law equality, which I already presented. We get something which is a generalization of the Jarzynski equation, which is valid not just if the state is thermal or if you perform a measurement. Again, this has appeared in the literature, but I think under only classical proofs, and we get a kind of a version of the Crookes equation. Good. How much time do I have, Fernando? Sorry? I have 15 minutes. Amazing. Are you sure? Yeah. Okay, I'll go to town then. Good. Okay, so let me discuss kind of where future directions and open questions. So I guess the thing here, and what I want to emphasize here is what are the tools from quantum information theory that we can apply to thermodynamics? I think that's what I liked about John Preskill's tutorial. He was able to point to different tools that we have in quantum information theory and show how they were useful in high energy physics. So let me talk about some of the things, the kind of tools we have in quantum information theory, and see how we can apply them in the thermodynamic case. So the first thing, and actuations of work, which is something that was considered in the stochastic thermodynamics community, but also fluctuations of states. And this was done in kind of the late 1990s by Bidal and Jonathan Plenio, who looked at probabilistic transformations under LOCC for quantum states. And we can use some of those results or adapt them in order to understand fluctuations of states. You can ask, what is the probability of going from one state rho to one state sigma? We can also consider different versions of the third law. So in computer science, we're used to considering time as a resource. And the third law, in some sense, the second law tells you, can I go from some state rho to some state sigma? And the third law is effectively saying, how much time does it cost, or what are the other resources that it takes to go from rho to sigma? So like a Turing machine, you can consider a thermal machine. So just like we make a physical version of this thermal device, and then ask how many steps it takes to, say, cool down a system. So we have those tools from computer science in order to understand the time it takes or the number of steps it takes to do a particular transformation. One can ask about different resources. So here, Reeve and Wolf looked at a finite-sized dimension heat bath and looked at cooling or erasure. In that case, here we're able to look at infinite dimensional heat baths and show that you get a third law where which depend on the work fluctuations, as I mentioned, that you need arbitrary large work fluctuations in order to cool something, and you need arbitrary large volume in order to cool something. So let's go to probabilistic transformations under, yeah? Sure?
Just jump. So you were saying something like probability half might go to one state, probability half might go to another state. You don't have a way to recover to which state you went to, right? Or perhaps you do, because otherwise it's just that you go to their convex combination. It's not that there's no state that you're, unless you know where you're going to, then you just go to their convex combination. There's no one state which you can say that you went to.
Right. So you can consider two cases. One is that you have what we call the heralded case, or which is something that Gilad Gore has since looked at, where you imagine that I have a state and I want to go to one of two states with a label attached to it, so I know which one I have. I might imagine that. Or I could imagine just that I want to go to some convex combination of two states and I want to maximize the probability in front of the other one. Or I could imagine that I want to go to a state which is the largest fidelity to a target state I'm interested in. So it may be that I'm not, so let me maybe pose the question like this, a bit more generally. So let's say that I can go from some state rho to some state sigma using an amount of work W. And now I'm going to say, I'm not going to let you use that W because you don't have a work system. So I quantify the amount of work. So I can go from rho to sigma if I have some work. But if I don't have work, can I go there? And the answer is no, you can't. But maybe you can go there with some fidelity or with some probability. So here, we're choosing a rather arbitrary measure. We're saying that what we want to do is we want to go to some state which we can write in some convex decomposition of the target state and some arbitrary state, and we're interested in maximizing the probability of going there. There's other measures you can choose. The fidelity is a kind of a natural one as well. So there's a number of different measures you can choose, and I'm not sure what the best one is. We did this way because we get you can kind of solve it fairly using some tools from entanglement theory. But the kind of question of, can I get close in fidelity to the state if I don't have enough work? That's kind of a harder question, but you can probably use similar tools to get that. So I think that's an open question as to how you should think of approximately going to a state.
Okay, thank you.
Okay. So here, we want to go to some state. We want to maximize the probability in the sense. We can think of the heralded case or the unheralded case, but here I'm just going to talk about the unheralded case. We just want that we can go to some state which has as large a possible P star to sigma. Okay? And I think what's nice about this result is that we're able to, we're able to get bounds on P star, which are in terms of the work cost. So the greater the work cost, the smaller the probability of getting to your target state. And in fact, the probability P star is bounded from below by the work cost going from rho to sigma, and bounded from above by the reverse process of going from sigma to rho. In the classical limit, if I take the thermodynamic limit where I go to many copies, then this just goes to 0. So in the classical limit, if it costs you work, in the thermodynamic limit, if it costs you work to go from some state rho to some state sigma, then there's just the probability of going there probabilistically is 0. Okay? So what's nice here is that you kind of, in the case of a finite size system, you can do that. And the idea is follows. Let us take as a measure these VLs. They're just basically the kind of like their little majorization. They're kind of the sum of the L largest probabilities, right? So they're kind of a measure on majorization. So here I'm just going to set the total energy to the Hamiltonian to be trivial. So I sum the L largest probabilities, and I get these measures VL, and P star turns out to be equal to the minimum of the ratio. All right? So for example, if I want to go from B to A, from A to B, then what I should look at is these different ratios of the vertical drop between my initial state and the final state. And that's because what's happening here for probabilistic transformation is that I'm allowed to change my majorization curve by just multiplying it by some probability, and I can drop the final state by scaling it by an amount P. All right? So the probability of the fluctuation is just given by the largest distance between the two curves. And the work is given by the vertical distance between the two curves. So in terms of how much work is required to go from B to A or A to B, it's just given by the smallest ratios here. And so this graphically allows you to, in some sense, bound the probability of a transformation by these vertical distances here. Joe's called this submajorization, and he's noted that this kind of version of majorization just corresponds to the question, is there a substochastic matrix which satisfies these conditions here? So again, another kind of generalization of majorization. Likewise, using this notion that the fluctuations, in some sense, if we're trying to physically do a process and the fluctuations grow very large, then it becomes harder and harder to do a process if the fluctuations in work become larger and larger. Right? So the heat theorem, originally given by Planck in 1911, says that when the temperature of a pure substance approaches absolute zero, its entropy approaches zero. The heat theorem has nothing to do with thermodynamics, as you will see. It just basically is the statement that the ground state should be non-degenerate. So that has nothing to do with thermodynamics, but to the Hamiltonian. The unattainability principle, on the other hand, which Nernst formulated in 1912, says that any thermodynamical process cannot attain absolute zero in a finite number of steps or within a finite time. And what we want to do is we want to quantify this, and it turns out we can quantify it in terms of the amount of work and how it fluctuates, and in terms of the volume of the heat bath. Okay. So let me end just by mentioning a few other kind of areas of kind of interest. So I mentioned that somehow these quantum Crookes relation that Johann gets and that we get, it looks like it's a statement about the Petz recovery map, and it's kind of interesting to kind of dig further into that and get a better sense of what that means and whether we can use some of our insights into, say, approximate recoverability to understand thermodynamics in better detail. There's also the question of what a cyclic process is, and that's something that's also not resolved. In thermodynamics, in the macroscopic limit, if you remember the Clausius statement of the second law, it was that heat can never pass from a hotter body to a colder body, or a colder body to a hotter body, without some other change occurring elsewhere. What do we mean by no other change occurring? Classically, you might think it means that that it should approximately be cyclic, but we know from embezzling of quantum states that that's not going to work. All right? That if you demand that something be approximately cyclic, you can always find some ancilla where you are approximately cyclic on that ancilla. You get arbitrarily close from its final state to its initial state, and yet you can extract some work from it. Just like in the entanglement embezzling, we go from some state to another state which is arbitrarily close to its initial state, and we get entanglement from it. So there seems to be an embezzling problem in thermodynamics, and it makes it almost impossible to define what we mean by a cyclic process. So that is, I think, an interesting open problem. With that, I'd like to thank you very much for your attention.
Thank you, Jonathan. We have time for questions. I see one over there.
So you put out the broadest set that is allowed in the thermodynamics that allows the most powerful scheme that, possible. But in that scheme, still you think about the unitary that commutes with the total Hamiltonian. But if you know the initial state, and if you think about the unitary that conserves the average energy, average energy given that initial state, then that would give you like more powerful like operation, I guess. So is there a reason why you you stick to the commuting condition?
Yeah, in some sense, because you don't conserve energy on average, you conserve it exactly, right? So in an actual system, you conserve it exactly. So if you're doing a operation which only conserves energy on average, it means that you are secretly smuggling in a little system which sometimes takes energy and sometimes doesn't take energy, but on average doesn't. And the amount of fluctuations that you're putting into that have to be arbitrarily large. So you're cheating a little bit when you just say that you only want to consider work on average. It means that you've smuggled in your system. Now, I don't mind that. If you want to have your system there which sometimes has work and sometimes doesn't. But I want you to account for it because I want to make everything, all these kinds of abstract notions like conserving on average, I want to make sure that we understand physically what's going on. And so in that case, I'll have this secret device which is taking on fluctuations arbitrarily large. In fact, in some sense, here I can consider it just by, my work system here is allowed to fluctuate, and I might care about the work only on average, and then I effectively get the paradigm where I only conserve energy on average.
So in your scheme, still like your battery, so the exact work fluctuates, right?
The work, in this paradigm you can consider so here it's just a paradigm of what we mean by thermodynamics. The quantities you want to consider are up to you. You may be interested in the average work, in which case, really in some sense you're conserving you're conserving energy. It's equivalent to thinking about conserving energy on average, but it's a bit more honest because you see how big the fluctuations have to be. On the other hand, you could also look at the deterministic work cost within this framework because you're just basically picking a different distribution of the kind of work you're interested in.
Thank you. Any other question? There.
I was wondering if any of these free energy, change in free energy results that you're talking about can be easily extended to holography through their usage of the modular Hamiltonian?
Yeah, so I actually have a work in progress with Rob Myers in the Perimeter Institute and some of his postdocs where we're looking at can we take these additional second laws and apply them to black hole systems or to gravitational systems. So we know that for black holes, you have the second law of thermodynamics, and if you ask what that means in terms of the black hole, it's that the area has to always be increasing. And now you know that these other laws of thermodynamics also have to hold, and you can ask if they have what the physical interpretation is on the gravity side. Now, it's difficult to answer that question. We tried a bit thinking in terms of quasi-normal modes of a black hole, or because here these apply to out of equilibrium systems, so you can imagine an out of equilibrium black hole. It turns out that that's difficult to see if that works. At the moment, we're doing the computation in the context of ADS-CFT because there in the CFT you know that these second laws have to apply, and you can ask they must if you believe in the correspondence, then they should correspond to something happening on the gravitational side. But the computation actually is quite difficult.
There was okay.
I have a so the question is, I'm interested if there is some experimental way of probing this higher order terms in second law that kind of you have this kind of extension of second law. So can it be seen experimentally in some experiments? Or?
Yeah. So I guess what these tell you is that normally people would tell you, well, the entropy. Let me use the entropy as an example. They would say the entropy has to increase, and that's what the second law says. But here we see we need these other conditions as well. And so it's possible that some of these could be violated, but the entropy could still increase. So they give you additional constraints, and you might want to say, can we see them in the lab? So for example, it may be that the largest eigenvalue gets higher, but the entropy still increases. Well, that's ruled out by these additional second laws. So I guess you can never show that you can confirm that you see them holding. Of course, you can never, it doesn't say that they're never violated, so you can't prove that, but you can at least show that they provide reasonable constraints.
Any other question? Yeah, John.
So you're using the Gibbs state as a free resource, but more fundamentally, the Gibbs state is derived from the second law of thermodynamics by maximizing the entropy of an overall system, and you look at the small system. Is there do you have a comment towards that derivation instead of going from Gibbs state to your second law?
So the derivation that we had for the Gibbs states, so we called it a zeroth law in some sense of thermodynamics. So this is in the paper with Fernando Brandao in 2015 in Proceedings of the National Academy of Science. What we claimed was so let's go back to the resource theory. I just said that you're allowed to add some free state and we don't tell you what it is. And now you can ask, what free state are you allowed? If you allow any state which is not the thermal state, then you can do everything. The theory becomes trivial because you can extract an arbitrarily large amount of work from it. So in some sense, you are just demanding that this resource theory be doesn't allow arbitrary work to be extracted is not trivial, forces you to make this free state the Gibbs state of a single temperature. So temperature naturally arises from the resource theoretic picture in terms of, it's the equivalence class of states you're allowed to add in the resource theory such that the resource theory is not trivial. So that's how I would frame the zeroth law and temperature emerging. It's not coming from the second law, it's just coming from stability of your resource theory.
Okay, I think our time is up. We have an announcement, but before that, let's thank Jonathan again.